Welcome to Casting Academy. Today our topic is materials and engineers. The questions for an engineering student towards material are: what do we with the materials? Why should we know about materials? What do we do with the materials? Why should we know about the materials? The answer is engineers converts material into products using energy to meet the needs of society. Convert the material into product for requirement of society. Engineers design products and systems, make them and monitor their usage. Engineers design products and systems, make them and monitor their usages. And a mechanical engineer involves in the design and production of an automobile. Bridge grader is designed and constructed by a civil engineer. Aerospace engineer develops a space shuttle. Chemical engineer constructs chemical plants. Since all these require materials, an engineer should be well informed about the materials. Engineers are in search for advanced materials to improve their design and create new products. High temperature resistant material for jet engine, high strength to low weight ratio material for an aircraft, highly corrosion resistant material for chemical equipment are few examples for this church. To develop new materials, the engineer has to design the internal structure of a material which provides the required properties. Structure and properties of materials. You see the cooling rate and harness number. In heat treatment process, processing, structure, properties and performance. They are interrelated. From the figure, the material property harness depends on structure. From the figure, so you see the material property depends on structure. The structure is modified by processing. Structure is modified by processing. So, structure and processing are interrelated. Here, the hierarchical order is processing, structure, properties, and performance. They are interrelated. Here, structure, performance, processing, properties. You see, materials engineering. Designing the structure to achieve specific properties of materials. In materials engineering, we are designing the structure to achieve specific properties of materials. But in the case of material science, investigating the relationship between the structure and the properties of material. Previous one is application, second one is research side. So this is the performance, processing, structure and properties. Structure of material. You see, this is a microstructure of material. So annealed steel submitted on cyclic torsion. The various properties of materials originate from its internal structure, only internal structure. So the knowledge of the internal structure of material, knowledge of the internal structure of material and how its structure correlates with the properties help the engineers in a big way. So knowledge of internal structure is a very much essential for engineer. The internal structure of material are studied at various levels such as atomic structure, crystal structure, substructure and microstructure. Internal structures studying in different way such as atomic structure, crystal structure, substructure and microstructure. Depending on the level, the magnification, depending on the level, the magnification and resolution of physical aid to study the internal structure also varies. The atomic structure, spectroscopic techniques, crystal structure, X-ray diffraction, substructure, electron microscope, microstructure, optical microscope with higher magnification. So these are all the atomic structure techniques. So microstructure of material you have now you are seeing. In this we are using these kind of approaches: X-ray diffraction, substructure, electron microscope and microstructure, optical microscope, etc. Now we are in a interesting topic of atomic structure. In your previous classes you study about the atom, molecules, proton, neutron, etc. Here the atomic structure is, you see, central one is the around orbits, so electrons are rotating in center part nucleus. Here any atom is composed of heavy nucleus surrounded by light electrons which revolve around the nucleus. Any atom is composed of heavy nucleus, so nucleus is here, that is surrounded by electrons. The nucleus contains protons positively charged and neutrons neutral particles, and electrons are negatively charged held to nucleus. The atomic number of an element is equivalent to the number of electrons of proton in each atom. The atomic number of an element is equal to the number of electrons of protons in each atom. For example, iron contains 26 electrons, 26 protons, and hence the atomic number is 26. So the electron number is the atomic number. The atomic mass of an element is the mass in grams, 6.023 into 10 power 23 atoms of the element. So as you know the in previous classes very broadly. So here the atomic structure. Next, electronic structure of the atom. Electronic structure of the atom. Electrons revolved in the group of orbital called the shells, spaced from each other. There is a limited number of electrons in any cell. For example, 2 in the first cell, 8 in the second cell. So in electronic structure, we have shell, orbit, and first orbit is 2, only 2, and second one is 8. The electronic structure of an atom is defined by 4 quantum number. 4 quantum number. Number 1, principal quantum number, that is n equal to 1, 2, 3, 4 up to 5, refers to the quantum number of the cell. Azimuthal quantum number, that is SPDF, refers to energy levels in each quantum cell. And magnetic quantum number 12 plus 1 specifies the spatial orientation of an atomic orbital. And last, electron spin quantum number, that is specifies 2 allowable spin directions for an electron. So based on the quantum number, electronic structure of an atom is designed for designated. For example, the notation of sodium, which has an atomic number is 11, is 1s square, 2s square, 2p6, 2 power 6, and with the 3s power 1. This is the sodium. Here, electronic structure and properties. The chemical properties of an element are closely related to the number of electrons outer orbit group in the outer orbit group. These are called the valence electrons. The chemical properties of an element are closely related to the number of electrons in the outer orbit group. These are called valence electrons. If an atom is completely filled with the outer shell, there is no valence electrons. Then the element is inert, which is not ready to react. For example, argon gas an electronic structure of 1s square, 2s square, 2p6, 3p6. The outer shell is completely filled, so it is chemically stable. So electronic structure properties. Where the outer cells are incomplete, there is a tendency for the elements combined chemically to form stable outer cells. So when vacancy in outer cell, the elements ready to react. For example, aluminum has an electronic structure 1s square, 2s square, 2p6 up to 3p1. Aluminum has three valence electrons in the outer sp levels. The chemical behavior of the aluminum is determined by this free reaction. This free electrons. So the chemical behavior is determined by the free electrons. The elements which gain few electrons to fill their outer energy level called electronegative elements. The elements which gain few electrons to fill their outer energy levels called the electronegative elements. The elements which readily give up electrons and empty the outer energy cell called electropositive elements. So readily give up electropositive and accepted is the electronegative. Next, atomic bonding. Atom is a material are held together by some sort of binding force. Bonding between the atom is essentially an electronic process. During bonding, there is a net decrease of potential energy. So the atom in the bonded state are in the more stable energy condition than unbonded state. The bonds between the atoms are divided into two groups. Primary bonds, ionic bond, covalent bond, metallic bond. Secondary bonds. So bond between the atoms is divided in two groups, primary and secondary. In primary, ionic bond, covalent bond and metallic bond. Ionic bond. First you see the figure first. So here the Na sodium chlorine atoms, electron transfer and the electrostatic attraction. So outer cell here sodium have one electrons that is accepted by the chlorine here. So ions. So outer cell electrons move into the chlorine cell, that is called ions, atom ions. Electron transfer. Here the bond is NaCl. Here the bond is NaCl. So that is called ionic bond. This is a non-directional bond. Here you see sodium gives one electron and accepted by the chlorine. So this is ionic bond. Here ionic bonds are formed between the highly electropositive elements and highly electronegative elements. Atoms of an electropositive element easily give up its valence electrons to the electronegative elements. The atom that gives up electrons to acquire positive charge is a cation, while the atoms that receives the electron becomes the negative is an anion. The oppositely charged ion attracted one another and form the ionic bond. An example of ionic bond is sodium chloride. The sodium atom has 11 electrons and chloride has 17 electrons. So in the ionization process, the sodium atom gives up 3 sp 1 electron and becomes cation. So the ions attract together to form strong bond. Here is the ionic bond. Next one is covalent bond. First you see the figure. So this is fluorine atom and carbon atom. So combination is gives the a molecular carbon molecule of carbon tetrafluoride. You see the transformation. What happened? Covalent bond is formed between two or more similar or dissimilar atoms by mutually sharing at least one electron among themselves to achieve stability. The shared electrons are considered to belong to the both atoms. For example, the molecules of carbon tetrafluoride, the carbon atom has four valence electrons, where each of the fluorine atom has seven electrons. So, the carbon and fluorine share the electrons of to form covalent bonds, and both of them get stabilized. So, here is the case covalent bond. Metallic bond. First, you see the figure. Negative electronic cloud, positive metal ion. You see the plus plus minus minus cation and anions. The metallic atom give up all valence electrons and become positive ion cores. The metallic atoms give up all their valence electrons and become positive ion cores. These electrons form an electronic cloud and move freely with the cloud and get bonded to positive ion cores. The positively charged ion cores are held together by mutual attraction of the free electrons, thus producing metallic bond. This is the case of metallic bond. Secondary bond. Atom A, atom B, what happen? High density clouds and high density clouds. So attraction is between plus minus electrons. Secondary bond obtained without the electron transfer or sharing. Without the electron transfer and sharing. The mechanism of secondary bonding called polarization is the separation of centers of the positive and negative charges in an electrically neutral atom as it is brought together to its neighbor. So some portions of the atom is positively charged while other portions are negatively charged. The electrostatic attraction between the positively charged region of one atom and the negatively charged region of the other atom is the secondary force. Here you see the positive and negative. So this is the secondary bond case. So bonding and properties. First you see the type of bonding. Ionic bond. So bonding energy is 632 1550 in kilojoule per mole. Direction non-directional. Covalent is 522 1260 directional. Metallic 100 to 800 non-directional and secondary less than 40. So this is bonding properties of atoms. Here what happen? The properties of the material depend on the bonding characteristics. Mainly, the properties of the material depend on the bonding characteristics. Melting temperature. The bonding energy is the energy required to create or break a bond. The materials having higher bonding energy tend to have higher melting point. It is understood that covalent and ionic bonds have higher binding energy than metallic bonds. Hence, the covalent ionic bonded materials have high melting points. Next, first case is melting temperature. Second case is mechanical properties. The strength and the directional natures of the bonding of mechanical properties. So, direction shows the mechanical properties. Solids which have strong and directional bonds tend to be hard and brittle. Covalent bonds are strong and directional and they are hard and brittle. For example, diamond. As metallic bonds are weak and non-direction, they are soft and malleable. Next, thermal and electrical conductivity. Thermal and electrical conductiveness of material largely depends on the free electrons. Ionic and covalent bonds results on inert gas configuration and there are no free electrons. So ionic and covalent bonded materials are good thermal and electrical insulators. Since the metal have free electrons, they are good conductors of heat and electricity. So this is bonding and properties. Next, structure of solids. Most of the engineering materials are solids. The physical structure of solid materials depends mainly on the arrangement of atoms, ions, or molecules which make up the solid. The atoms or ions of solid are arranged in repetitive three-dimensional pattern. They form solid which said to be have a crystal structure and is referred to crystalline solid. If the atoms of ions or solid are arranged in repetitive, then it is a crystalline solid. Crystalline solid not have such repetitive three-dimensional platform pattern atoms and are called non-crystalline. So repetitive pattern crystalline, non-repetitive pattern non-crystalline. Metals of some ceramics have crystalline structure and other ceramics or polymers are classified as non-crystalline solids. Here is the crystal structure. First you see this is the structure of arrangement of atoms. The regular repetitive arrangement of the atoms described by three-dimensional network called space lattice. So this one is called space lattice. Space lattice is a three-dimensional pattern of points called lattice points. Each point in space lattice has identical surroundings. The smallest component of the space lattice is unit cell that retains the overall characteristics of the space lattice. The size and shape of the unit cell is described by three edges. Edge length is A, B, C and the internal axis angles are alpha, beta, gamma known as lattice parameters. So as you know, arrangement of atoms is based upon lattice parameters. Here the Brave lattice. According to the lattice parameter, there are 7 crystal systems having 14 types of space lattice called Bravis lattices. 7 crystal systems and having 14 types of space lattices, that is called Bravis lattices. So first you see one by one. This one is cubic. So edge lengths are AB equal to C, all are equal, and angle between the ABC equal to alpha, beta, gamma equal to 90 degree. So this is cubic. Then the same case with the body centered cubic. This case is face centered cubic and tetragonal. So alpha, beta, gamma equal to 90 degree. This is also body centered. Orthorhombic. A equal to B not equal to C. So alpha, beta, gamma that is equal to 90 degree. So this is the different cases. In hexagonal, A equal to B but B equal to not C. And trigonal, monoclinic, A not equal to B not equal to C, and alpha and gamma equal to 90 degree, beta equal to 120 degree. So this is the Bravais lattices. So types of unit cell.